Okay, so we are on day 2 of section 5.2, the strengths of acids and bases. And today we're going to be comparing the strengths of acids and bases. Remember that Ka is for weak acids, and the larger your Ka value, the greater the hydronium ion concentration. Kb is for weak bases, so the greater the Kb, the higher the hydroxide ion concentration. So we're going to be looking at a table on the following page. It takes up the entire page. And we're going to be sort of making some notes on how to tell if something is strong or weak and what the subsequent Ka and Kb values are. So you're going to have the acids listed on the left-hand side of the table, and the conjugate bases will be listed on the right. So let's go ahead and turn the page. And I have a lot of notes to make, so I'm just going to kind of make them from top to bottom as we move throughout. Okay, so let's start out with some of the strong acids. So here at the very top, you have your strong acids 1, 2, 3, 4, 5, and 6. So this is perchloric, hydroiodic, hydrobromic, hydrochloric, nitric, and sulfuric. You will notice that the arrows that they have are pointing in one direction here, right? And it's like this sort of gray shaded region, which is where your strong acids lie. We're clear on that? Okay, so all the way down on this left-hand side are your acids, but only these really, really strong ones are here listed at the top. Okay, so what differentiates a strong acid from a weak acid? You know that strong acids are 100% ionized, therefore they're sort of more willing to donate a hydrogen ion. So I want you to make a note that these are more willing to donate a hydrogen ion. In fact, these are completely willing to donate a hydrogen ion because they are the strong acids. Does that make sense? So underneath the strong acids down here, you will notice, let me make this a little bit smaller so we can kind of see all of them. There's a lot going on here, right? So underneath, you've got, starting with the hydronium ion here, all the way down to water. Okay? So hydronium ion down to water. These are all technically weak acids. So hydronium ion down to water are all weak acids. They are arranged in increasing order of strength. So you'll notice down here, these are like the really, really, really weak acids. Weak acids. Does that make sense? And then as I go up higher, they're increasing in strength. So even though these are all weak acids between the hydronium ion and water, they are arranged as the weakest of the weak are down here. And the stronger of the weak are here. Does that make sense? So up here, these would be stronger weak acids, and these would be the weakest of the weak acids. I just want to make sure that this makes sense. We're good? Okay. What you will also notice is we no longer have the single arrows pointing in the direction of the ions on the right-hand side. We have our double equilibrium arrows for all of these weak acids. Good? Okay. So let me just pose a question to you. Which acid would be more willing to give up a hydrogen ion? Nitrous acid or boric acid? Nitrous acid, right? Because it's stronger. Okay. Okay, now let's take a look over here on the right-hand side. On the right-hand side, you've got the conjugate bases. So over here you had acids, and over here you have their conjugate bases. The conjugate bases of the strong acids have Ka values that are so large that they're not even useful. Therefore, they do not include them. It only says very large, like right here. Okay? So these actually do not act. Let's just make a little note here. These do not act as weak bases. Okay, so the conjugate bases of the strong acids do not act as weak bases. When we're looking at all of underneath them, you will see starting here, just underneath the shaded region at the top, going all the way down to the bottom. Here you've got your weak, God bless you, your weak bases here, and they're increasing in strength as you go down to the bottom. God bless you. Okay, now, for the strong bases tend to accept hydrogen ions. Like they are very, very, very willing to accept a hydrogen ion. Whereas up here, these weak bases, are kind of reluctant to accept a hydrogen ion. They're like, I think I'm better off without it. Thanks. Okay? So if I said to you, which is the stronger base? The nitrite ion or the cyanide ion? Cyanide. Right, so cyanide would want to accept a hydrogen ion, more so than the other one. Okay? Let me point out a couple of other things. We have a substance that is amphiprotic. It's hard to see on here because it's so small, but the bicarbonate here and here. Do you see this hydrogen carbonate ion in two different places on the acid and the conjugate base side? Label that because it is amphiprotic. That means it can accept or donate. If you can't see it, it's HCO3 -1. It's an amphiprotic substance. It's labeled as the hydrogen carbonate ion on the left-hand side towards the bottom. And then one other note I'd like you to make down at the bottom here is you've got two ions down here on the left-hand side. Actually, one's an ion, one's a neutral compound. They are not marked as acids. So I don't want you to label them as such. They do not act as acids in water. So this is ammonia, and what does that say? Hydroxide ion, that's what I thought it said. So these do not act as acids in water, okay? Well, ammonia we discussed the other day, right? Ammonia is a base. It does not act as an acid in water, okay? Okay, does this table, God bless you, does this table make more sense now that we've labeled it? we're going to use it for the rest of class. Yeah.
So on the acid side, we have them all as weak acids, but you don't have that on the base side, like them all as weak bases. They're just stronger than the others.
That's correct. That's correct. They don't have like potassium hydroxide because these are conjugate bases. So these are where something had lost a hydrogen ion. And so things like potassium hydroxide, magnesium hydroxide, sodium hydroxide, things that you know are strong bases, they don't have a corresponding sort of like conjugate. Does that make sense? So that's why they're not listed here. Yeah.
So for the conjugate basis side, where you mark the acids, you said they don't act as acids initial. For the conjugate basis side, would that be compacted by chance? Do they not act as bases in water, or is that just ignore that?
Ammonia is a base. Ammonia is actually listed right here. See how it says NH3?
Mm-hmm.
So I'm not sure how to answer
So are the bottom
your
two
question.
just aren't acids?
The bottom two just aren't acids.
Okay.
Does that help?
Yeah.
Sort of, for now?
For now.
Okay. Let's do some practice problems. You guys tired? Let's look at the quick check here. I'm just going to keep it like this because I think it's easier to make a reference back to the table. I will give you this table on a test and the final. Okay? I would never prohibit you from using it. Okay? Okay, yeah.
Are the bullet points just kind of outlining the table?
Yes, the bullet points outline basically everything that I just said. Okay. Quick check. Classify the following as a strong acid, strong base, weak acid, or weak base. Why don't you take a look at A through F with the person sitting next to you and label them.
So do you want to stay on the other side, or do you want me to?
Sure. I think it's fine.
So here could be strong. Strong acid. It's one of the
Yeah.
top ones. Also play oxide. I think calcium hydroxide is the best.
That's
Thank you.
I was like all good one too with the hydroxide. Those are like the strongest.
I don't think it's all of them, but like the heavier ones. I believe yes. That's back on page what? They're all listed in the back on 273. Bottom paragraph. All the strong bases.
Yeah, that's where I remember it. That's where I think ammonia it's a base.
Yes, it
Like
is.
a weak acid.
It is.
Thank you for reassuring me, Mr. Walter. I'm like a scrambled egg right now.
It's
I
okay.
had 3 tests other than this quiz today. So I've had 4 today, and I'm just done. I can't do it.
I understand.
Benzoic acid. Benzoic. Oh, benzoic's in the middle of the weak acids. So it would be like a moderate acid.
Okay, are we ready? What'd you get for sulfuric acid?
Strong acid.
Strong acid, good job. How about calcium hydroxide?
Strong base.
Strong base. Ammonia?
Weak base.
Weak base, we talked about that the other day. Benzoic acid. Weak acid. Cyanide ion.
I wouldn't think of any of these.
Cyanide. CN -1.
Is it any of
It's still okay. It's still a weak base. Okay. Let's go over here for a second.
So I was confused.
Okay. These are all weak bases. This is the weakest of the weak. This is the strongest of the weak. Do you follow? So it's still a weak base. Confusing? Or are we okay? Yeah.
Where are the strong bases?
Well, we don't have things like the ones that you memorized back on the second page. If we turn back to page 273, NaOH, KOH, CaOH2, MgOH2, they aren't on.
So all
Okay, you just need to memorize those.
okay, so all the ones on the chart are just weak bases? And
Yes.
that's how-
Except for these two down, well, yes, yes, yes. Okay, how about nitrous acid? Weak acid. Okay. Okay, now, question number 2 says, for the weak acids or bases above, write an equation demonstrating their behavior in water and their corresponding Ka or Kb expression. Well, why don't we just look at a couple of them? Why don't we look at ammonia and the cyanide ion only? Or actually, why don't we look at one of each? Let's look at the weak base ammonia and the weak acid nitrous acid. That way we can do one of each. Okay? So if you're looking at ammonia, ammonia is ammonia, not ammonium. NH3 is ammonia. Okay, so if you have ammonia in water, what am I going to form? NH4 plus 1 and OH negative 1, because ammonia is a base. That means water is going to give a hydrogen to it, right? And that means that your Kb would be NH4 plus 1 times OH negative 1 divided by NH3. We omitted water. If we're doing nitrous acid, what's the formula for nitrous acid? HNO2. Good job. HNO2. In water. That means it will give a hydrogen to water, and you're going to form NO2 negative 1 and H3O plus 1. So what is your corresponding Ka? NO2 times H3O plus 1 divided by HNO2. Okay. Back to the questions about where are the strong bases. Do the strong bases have a Kb?
No.
So it would make sense that they wouldn't be in that table also. Does that make sense to you guys? Because these are all substances that essentially have Kas. Okay, there are no Kbs listed here. And, okay. Take a look at number 3. A student tests the electrical conductivity of 0.5 molar solutions of the following: carbonic acid, methanoic acid, phenol, and boric acid. Rank the solutions in order from most conductive to least conductive. Why don't you do that with the person sitting next to you, and let's see what you come up with.
Is that methanoic carbonic? Wait, no, these go. So this one.
Okay, so this is what I got carbonic as second, methonic as first, phenol as fourth, and boric as third.
Okay, I got methanoic acid was first, carbonic was second, boric was third, phenol was last. Any questions on that stuff? Nope? Okay. Let's turn to the position of equilibrium and relative strengths. Okay, if you have a if you have an acid and a base reacting, we can predict whether the reactants are favored or the products are favored depending upon which side has the stronger acid and base. You can also think of this as if my KEQ is greater than 1, then my products are favored. If my KEQ is less than 1, my reactants are favored. So since acids and bases are going to, or since acids that are really, really strong are going to get rid of a hydrogen ion, or they're more likely to get rid of a hydrogen ion, that means that the equilibrium position is going to actually be predicted by which side has the stronger acid and the base. So if we're looking at this example here, what I want you to do is take a look at this NH3 base versus this HCOO -1 base. Turn back to the table that we just finished labeling, and I want you to tell me which is stronger. Look on the right-hand side. Is NH3 a stronger base, meaning further down on the right, than HCOO -1? Yeah. So that means that NH3 would be my stronger base. And then I want you to compare the acid. Take a look at the left-hand side at HCOOH and NH4 + 1. Which one of those is further up on the left-hand side? HCOOH. So that means that this one is the stronger acid. So equilibrium will favor you moving from the stronger acid and base side to the weaker acid and base side. Okay, so in this case, that's what I'm doing. Aren't I moving from the stronger acid and base to a weaker acid and base as I go from left to right? So that means that the products would be favored for this process, and the forward, or we could say the forward reaction is favored, okay? Sometimes you may see this labeled as an arrow proceeding further to the right than to the left. It just depends upon what textbook you're looking at or online resource, okay? All right, do you want to do another example like this? Okay, let's take a look at the sample problem here. And I'm just going to walk you through this like from the very beginning so you understand how to predict the products if the products aren't given to you. So here it says, predict whether reactants or products are going to be favored when HCN reacts with HCO3 -1. Okay, so what I need to do is I need to look at these two substances back on the table. So let's go back to the table. You're looking on the left-hand side. Let's see if we can find both of them. We're looking for HCN, which is down here. And then you're comparing HCN with HCO3 -1. Do we see HCO3 -1? We do. It's right here. So which one is stronger? HCN. That means it has a greater tendency to give up a hydrogen ion That means when we're doing this practice problem, or this sample problem, I should say, that means that you would label the HCN as the acid, and then the other substance would be the base. Does it make sense how I did that? Because HCN is a stronger acid than HCO3 -1. It will tend to give up that hydrogen ion more than the other one. That's why you label HCN as the acid. Once you've done that, then you can predict your products. If HCN is an acid, it will give up a hydrogen. It will form CN -1. That will be the conjugate base. If HCO3 is a base, its partner will be the conjugate acid. It's going to accept. We're good so far? Now we want to predict whether the reactants or products are favored. So now we have to go back to that table. And on that table, you want to look and see, how do the acids compare? So we're going to be comparing these two acids, HCN and H2CO3. Which acid is further up on the left-hand side? H2CO3. So if this is the stronger acid of the two, now we need to compare the bases. Which of the two bases is further to the right and down?
CN.
CN -1. So this is your stronger base. So that means we're going to move from the stronger acid base side to the weaker acid base side. So that's why my reactants are favored. And that means you could write that as like a little tiny arrow going to the product side and a bigger arrow going towards the reactant side. So the reverse reaction is favored. Make sense? Okay, do you want me to do one more practice problem with you, or are you ready to do one on your own? Do it on your own, okay. Let's turn to the practice problems. I want you to cross out 1A. I think they made a mistake, so we're just gonna go straight to 1B. So why don't you try 1B with the person sitting next to you. Do it the exact same way that we just did the sample problem. Yeah. Yeah.
I just literally write it out.
I start out with that much? Yeah? Okay, so if this is acting as an acid, then it's going to form H2C6, H5O7, negative 1. Agreed? And if this acts as a base, it will form NH4 plus 1. Do I have you so far? Okay. Now you have to look back at the table and you need to compare the acids. You need to see which one is the stronger acid, and then you need to see which one is the stronger base. So citric acid is a stronger acid than the ammonium ion. Agreed?
Yes.
So since this is the stronger acid, and out of these two bases, isn't ammonia the stronger base?
Yes.
So if this is the stronger base, that means your products are favored. Yeah?
Do you want us to write forward reaction favored? and,
Which, or it just depends on the question.
okay.
Yeah. So,
I have a question.
yeah.
So when the products are favored, it's a forward reaction.
Correct.
Okay.
And when the reactants are favored, it's a reverse. And then if you were to write this with arrows, you'd have a bigger arrow proceeding to the right than to the left. And then one more question, what about your KEQ? What would that be? Would it be less than 1 or greater than 1 if the products are favored? Greater than 1. I'm just trying to summarize everything so that you have it. Okay? Do you want to do another one like that, or do you want to do one that's a little bit different, maybe the same? Different? Why don't we go to number 3? We'll finish with 3. Consider the reaction between the sulfite ion and the hexaquochromium ion.
It's a cute little mouthful.
That's a total mouthful. So the sulfate ion is SO3, negative 2, and your hexaquochromium is chromium with 6 waters attached and a +3 charge. Okay? Let's look at the left-hand side of our table to see which one of those will act as the acid. So you'll notice that the hexaquochromium ion is actually listed as an acid, whereas SO3 negative 2 is not. I cannot spell. There we go. So that means that this will act as your acid. This will act as your base. Okay? So you'll get HSO3 negative 1, and then you'll get CrH2O5OH plus 2, like this, and this will be your base. Okay. Now, if we compare the two acids together, out of these two acids, this acid is higher on that table, so that means this is the stronger acid. So if it's higher on the left-hand side, it's a stronger acid, a stronger weak acid, right? And that means that out of my bases, my SO3 negative 2 and the other one, this is actually the stronger base. It's further on the right and down. So we move from stronger to weaker. So that means your products would be favored. And your KEQ would be greater than 1. Okay, does this make sense?
Yeah. So if the reactants are favored, your KEQ is less.
I'm sorry, what?
If your reactants are favored, your KEQ is less than 1.
Yes, if reactants are favored, KEQ is less than 1.